So we've seen how we can evaluate our model's performance, or at least initial performance, on something like epoch accuracy and epoch loss, and see how we can track different experiments. But this is just on the model's training and validation sets. And it's only really on what the model has learned in the data set. What are other really good way to evaluate what our model has learned is to use it for what we're building it for. If we're building dog vision, and we always got to keep in mind what the end goal is with whatever project we're working on. We're building dog vision to see if we can build a machine learning model that can identify a dog breed in a photo. So it's going to make some predictions giving a photo. So let's do that. If we come back to have a look at our workflow, well, we fit the model to the data. Now it's time to make a prediction. So we're still in step 3. We've done a little bit. We've touched on step 4. And remember, these aren't really linear steps. So these are just, I've just put them here because it's easy to understand it like this. But remember, they aren't necessarily linear, so you can do them out of order. We come back, we'll make a little heading. Making and evaluating predictions using a trained model. Command MM for turning it into Markdown, Shift and Enter. Okay. So making predictions with a trained model is very similar to how we did it in scikit-learn. So we can call the predict function and pass it data in the same format the model was trained on. That's the important thing. Let's see the code first, and then we'll discuss what's happening. So make predictions on the validation data. So remember, we created a validation data batch. Now, this was not used to train on. That's the important point. If we come back to our 3 sets, how we evaluate a model is because it trains on the training set. We want to check it out, its initial results on the validation set, and then both of these exams, so the practice exam and the final exam, are data sets that the model hasn't seen before. So we come back, let's go model, or actually we'll save it to predictions. Predictions equal model.predict val data, because let's just remind ourselves of what val data is. Val data, batch data set, there we go. We've got some images and some labels. So we know what the true labels are of the validation. So when we pass this batch data set to model.predict, because of the nature of the predict function, it's only going to look at the images in val data and then make predictions based on those images. So then what we can do is compare those predictions, which are going to be in the form of labels. Well, not exactly. We're going to see what they look like in a second. We can compare the model's predictions that it makes on the validation images to the actual labels from the validation images. Now, that was a lot of talking. It's much better to see this in code. So verbose is just going to say, hey, when you're making predictions, show me your progress. Well, that was really quick because we've got 200 images. So that's the beauty of working on a GPU. Predictions are really fast as well. And so that only took about 187 milliseconds. So not even a whole second. And if we didn't set verbose to equal 1, we wouldn't get this little progress bar outputting. You might be looking at this and going, what is going on here? Lots of just different numbers. So let's check out the shape here, prediction shape. If you remember, where does this line up? So if we go len, y, val, 200. So there's the first shape, so 200 images. Where do you think the second shape is coming from? 120, where have we seen that before? Len unique breeds. 120. So this means that we've got an array of 200 by 120. So we have 200, let's see the first element. So we have 200, we'll go predictions, 0. 200 arrays of 120 different numbers that are really small. And we're wondering what is going on here. Well, let's find out the length of this. 120. Wonderful. So what this actually is an associated probability for the likeliness, so basically what our model thinks a certain image is. So there's a probability value here for every single label. So the value here, the highest value in this predictions array, so the 0th predictions array, this is for one image, the first image in the validation data. So the highest value in here is going to correspond to the index of the label that the model thinks is most likely. And again, this is a lot of talking. It's going to make a bit more sense once we start to put it together with code. But just bear with me for a second. If we sum up all of these, they're going to equal very close to 1, or maybe 1 exactly. And I say very close because the way computers store numbers is not exactly. So if you keep going decimal points, right, it's going to get very close to 1, but it might not be exactly 1. And you might be saying, Daniel, what are you telling me this? The way the computers store numbers is not exact. Well, I don't even fully understand it, but you just have to know that when a computer stores a number that has lots of decimals, because of the way it's most efficient to actually store it on a computer chip, it's not going to be perfectly exact. So that's why I say when you sum up a single prediction array, it's going to be very close to 1. And now I'm going to tie this back up into where we've come back into our model. This is why we've used softmax activation. You might be saying, Daniel, far out, this is videos ago. You've already told us about softmax. It didn't really make sense, and it's really not making sense now. But if we go back to softmax, we just go, yeah, how about we go, what is softmax? If we come back to our friendly Wikipedia page, it's going to tell us that, but after applying softmax, each component will be in the interval between 0 to 1, and the components will add up to 1. So that is what we're getting here. We're getting our components, because we've used a softmax activation in the last layer of our network, it's outputted an array, a prediction array, that is 120 in length, and all of these values in prediction 0 and each other prediction here. So predictions 1 will be very close to 1 as well. So predictions 1 add up to 1. Or very close to 1. Oh, predictions. There we go. See, this is just over 1. So very close to 1. The more decimals there are, the less exact a number is with a computer. And so let's put this all together. Because right now it's just been a lot of talking. I want to show you a concrete example. Let's take prediction 0. So we're going to remove these cells. And just one little tidbit as well. Remember our MobileNet v2 architecture? All that our softmax layer is doing is taking these 1280 output, this array of numbers, and changing it into an array of numbers like this, of length 120, using a softmax activation. Because remember, for multi-class classification problems, we want a softmax activation. But if we were doing only single classification, we'd use sigmoid. So we come back here. Let's check it out. So the first prediction, I'm going to type out a few little indexing tricks here. And I just want you to just watch on. I'll talk through it a little bit as it goes. But I want you to start thinking about how these things all tie together. So let's do it. Because what our goal now is, our model has made some predictions here, but our goal is to understand these predictions further. Our computer understands these, right? Because they're all numeric. So remember at the start how we spent a lot of time turning our data into numbers? Kind of when you get to the output of a machine learning model, right? So this is what we're focused on. We spent a lot of time preparing our inputs. Now we're going to spend a lot of time preparing our outputs, which is what we're doing now. So let's go print prediction 0. And then what we're going to do is go find the max value probability. So remember the function in scikit-learn you might not, called predict_proba, which outputs a prediction probability. This is what predict does by default in TensorFlow. We go here, prediction, NP, max, predictions 0. So we're finding, let's remind ourselves, prediction 0, what it looks like. We're finding the max value in here. That's all that line does. And then what are we going to do next? So print, we want to, what else do we want? We want to find the sum. So NP, or actually, we might set this up so we can do multiple. So index equals 0, just so we can see it with multiple examples. So the sum. Sum is going to be NP sum, predictions, index, nice and simple. Then we're going to go, wow, that was a terrible typo, Daniel, come on. We're going to go the max index. So find the index in this array which has the max value. So which is equal to max value. NP argmax, predictions, index. And of course, what we're doing now is a little bit tedious. We're going to functionize this later on. So you could imagine if we just kept writing cells like this is where we're functionizing all of our code as much as we can, so that we don't just have to continually write these type of print statements to explore our data or explore our predictions. Predictions, index. Wonderful. Predicted label. Now before we run this cell, we're going against our cardinal rule of if in doubt, run the code. I want you to just have a think about what this one is doing. Let me remind you of what unique breeds is. So these are all our dog breeds. So if we have predictions and we find the max index of it, and then we find where that index occurs in unique breeds, what do you think that will return? Hint, we've typed it out here. All right, let's delete this bad boy, and then we'll shift and enter. Wonderful. So here's index 0. This is that array, just the exact same here. The output of our model when we call predict. So the max value, the probability of prediction, the maximum this can be is 1, because remember, the total of a softmax function is between 0 and 1, so the highest a single value can be is 1. So this is saying we're predicting the highest label in here with a 21.6% prediction probability. Now the sum of all of these values is very close to 1, again, aligning with the softmax rule between 0 and 1, and will add up to 1, but because of how computers calculate numbers, not exactly 1. And the maximum index, so where this value occurs, is 17. So if we counted through, we find 17, it's somewhere maybe there, that's it. Now, the predicted label is border terrier. So for index 0, or for validation image 0, the predicted label is border terrier. Now let's change this up. What if we did index, what's our favorite number? 42. So we got max value, probability of prediction. So this is a lot higher. This is 75%, so it's pretty confident with this one. So you could say the higher this value is to 1, the closer it is to 1, the more confident a model is about a certain prediction. The sum is very close to 1, the maximum index is 113, and the predicted label is Walkerhound. So if we go here, unique breeds, if we were to find index number 113, we would find Walkerhound. There we go, Walkerhound. 113. Walkerhound. So this is how we convert our prediction probabilities in numeric form, something that our computer understands, to something that we understand, a predicted label. So now we've got a kind of way to turn our predictions into something that we can understand. What we'll start to do next is we'll create a bit of a function that's going to allow us to find the predicted labels for every sample in the validation set. So about 200 or so images. And then we're going to unbatch this data set, the validation data, and compare the predictions in a visual way to the truth labels. Now again, a lot of talking, but in the next video, we'll start to build out that functionality and we'll see what it looks like in reality. And I'm so excited, right? Because one of the funnest parts is comparing your model's predictions with what's actually going on. Dog vision is coming to life!